we'll use electrical fields to describe the potential, which we use in circuits quite a bit. And we'll have some problems that are very similar to ones that we had for forces, vector problems, 2D vector problems. So you're almost certain to see a 2D vector problem on the test. And not this week, but it's next week, correct?
The 7th.
The 7th, which is next Friday, 1 week from Friday. All right. So the electric field exists in the space surrounding a charged object. And we define the electric field, which I'll call E. It is a vector quantity. We define it as the force divided by Q naught. And Q naught is this imaginary positive test charge. It's an imaginary positive test charge. When I was in high school, I had this physics teacher, Miss Perry, Mama Perry we called her, because she was, I don't know, she sort of looked like a mama, and she worked on tractors a lot, but she was a really good physics teacher. And she always said that you should carry two things in your back pocket. If y'all remember what the two things are, I think I've told you. One of them is your right hand, right? You should always carry your right hand in your back pocket in case you need it for what? The right hand rule. Right. And then the other thing is a positive test charge. You should always carry a positive test charge in your back pocket, because we'll use the positive test charge to determine the strength and the magnitude, the strength and the direction of an electric field. So this positive test charge, it's nothing real. It's not a real charge. It's just something imaginary, but you use it to determine the direction of the electric field. I'll show you how we do that in just a bit. It turns out that the magnitude of that positive test charge fortunately doesn't mean anything to the magnitude of the electric field, as you'd imagine, because, well, it's imaginary, right? So it shouldn't have any impact on the actual electric field. The units of the electric field, if we look at the definition of the electric field, the units should be in what? It's force per unit charge, so the units would be newtons over coulombs. Newtons over coulombs. Or, we'll see this a little bit later. I'm going to use newtons per coulomb right now, but you might also see the units in volts per meter. And that'll become clearer later. Volts is a measure of something we call potential or voltage, and it'll be related to the electric field by position, so we get volts per meter. All right, but just for now, we'll use newtons per coulomb, which is the force per unit charge. And whenever you have a charge within an electric field, then the force that the charge feels, just from the definition of an electric field, is equal to Q times the electric field. So let's try this little quick test. If I have a proton accelerated from rest and an electric field of 100 volts per meter, what is the velocity of the proton after 2 seconds? I'm just going to remind you of a couple things. First, the charge of a proton is equal to 1e, and y'all remember what the fundamental unit of charge is. I know that the force is Q times E. I also know that force by Newton's second law is ma. And then I have my kinematics equations. X equals v naught t. It's 1/2 at squared, and v is equal to v naught plus at. So try this out. I have a charge in an electric field, and I just want to know what is the velocity after 2 seconds. This proton after 2 seconds. And I give you the mass of the proton here. What's that, Ashley? I didn't say. It's not at 1:30.
Oh.
Right.
Big number.
Now, it looks like all my numbers exceed the speed of light, so just discard all reality when you're working this.
Except for C.
Right, except for speed.
Doesn't speed of light 3.0 times 10 to the 8.
Mm-hmm.
Okay. Trying to get numbers in my head, right?
That's a good number to know.
It's been a Christmas season, the break since last spring.
So your first step here is going to be able to find the force, and then you'll find the acceleration, and then you can find its velocity. Try to wrap this up. We'll come up to you in about 5 minutes. Feel free to share your answers if you want to talk about it. About 15 more seconds, or if you don't know, just guess. I'm going to stop at 5 minutes. All right, let's see. Looks like most people put B. I'm going to assume that's the right answer. We'll work through it real quick. Pretty sure that's right. So your first thing is to find the force. F is equal to QE. By the way, this seems just sort of like an exercise, but this is a pretty common thing when you want to move charges around. You use electric fields to move those charges. So like common applications of this are like in cathode ray tubes, which we don't really use so much anymore, but like the old TVs, they used electric fields to move a beam of electrons. Also in inkjet printers, they have these little drops of ink that go through these two metal plates that have an electric field between them, and they modulate the electric field depending on where you want the ink to land on the paper. And so it's a basic kinematics problem, but you have to figure out what is the velocity of the inkjet, or the little drops of ink, in order to find out where they'll land onto the paper. So it's not just an exercise. These are pretty common things you find in the lab. So let's see, if we want to know F, we say 1.6 times 10 to the minus 15. That's our Q for the proton. It's positive. And then E was 100. I'm going to put it in newtons per coulomb, but notice it can be in volts per meter. So that's what? 160 times 10 to the minus 19. That's in newtons. And then if I want to know my acceleration, it's F over m. So it's that 160 times 10 to the minus 19 divided by my mass, which is 1.67. That's the mass of a proton. That number is on your equation sheet, but it's a good number just to have in your mind. You use it quite a bit, I imagine. Oh, from E right here. 1.6 times 10 to the minus 19 times 100 is 160 times 10 to the minus 19. You might have 1.6 times 10 to the what? Minus 17. And I get, oh goodness, 9.58 times 10 to the, somebody help me out here? 3, 6, 9. 9, yeah. So that's my acceleration. And then I just want to know its velocity after 2 seconds. So it's a simple kinematics problem. This is 0 because it's at rest. So it's that acceleration times 2, which is 19 times 10 to the 9, or 1.9 times 10 to the 10, which is B, as most of you put. All right. There are some kinematics problems in the homework. 1 or 2 kinematics problems. You could see it on the exam. Y'all okay with this? The only application that's new here is finding the force due to the electric field. I'll give y'all just a second. Now we want to derive an expression for the magnitude of the electric field. So if I have a collection of charges, or if I have a single charge, and I want to find the electric field due to that single charge, then I need to know how to do that. So let's look at that, and then we'll move into collections of charges, where we'll do some integral calculus like we did last semester, volume integrals and the like. All right, so Coulombs Law gives the force between the charge Q and the test charge Q naught. So I'm going to have a charge Q, and then I'm going to have my little imaginary test charge. I'm going to draw a dotted line around it. So this is an imaginary charge. But I'm going to use it to determine the electric field at that point, where that imaginary test charge is. So this is imaginary. Can you just imagine that charge? Use your imagination to imagine this test charge right there. All right, so Coulomb's law gives the force between it. Remember Coulomb's law. K, Q, Q naught divided by what? The distance between them squared. It's not the radius, it's the distance between the charges. But we call it R. It is radial. I mean, I think that's why we use R, but it's not exactly radius. All right, so that gives us the force. And then remember our definition of the electric field is F over Q naught. So if we combine these two, then we say the electric field is F, which is K, Q, Q naught over R squared divided by Q naught. Notice that our imaginary test charge goes away, and so then we get an expression for E, which is just KQ over R squared. Now this is the electric field at this point, at the location of where your imaginary test charge is. And this is the magnitude of that electric field. Is KQ over R squared. So anytime we have a single point charge, which we'll have in quite a few cases, and in chemistry you deal with single point charges quite a bit as well, this is what we'll use to find the electric field, KQ over R squared. And this is just based on our definition of electric field, which that's just really a construct. It's just something that we use to describe the force. And then also on Coulomb's law, which is a law that we've observed to be true many times over. All right, can we be on this? All right, let's apply it. All right, so the E field is not dependent upon which quantity? It's not dependent upon the test charge. right? Which is good because that test charge doesn't really exist, and so it shouldn't impact the electric field at all. The electric field, or excuse me, the test charge is only a tool to sample or measure or sample the E field. We'll talk about this imaginary test charge quite a bit because we'll also use the test charge to find the direction of our electric field. I'll go down from here. And so let's look at that direction. And this is sort of where that test charge comes in. So the direction of the electric field is the same as the direction of the force, the electric force, on the imaginary test charge Q naught. So for example, if I had a positive charge right here, what would be the direction of my force on Q naught? Would it be to the left or to the right? If I had a positive charge right here, what would be the direction of the force on this charge? Would it be to the left or the right? I have a positive charge here and a positive charge here. How are they going to be? Attracted or repelled? They're going to be repelled. So my force on Q naught is going to be in that direction. So my force is in that direction. All right, so what is the direction of my electric field at that point? It's to the left or right? Yeah, it's to the right, yeah, so it's positive. So my electric field is also in this direction. So remember, my electric field is defined as the force over Q naught. So the electric field is in the same direction as the force, just based on that definition. And the electric field is just sampling the force field. It's just a tool to determine what is the force on a charge around another charge. Now similarly, what if I had a negative charge here? What would be the direction of the force on this charge, left or right? It would be to the left, right. Those are opposite charges, a negative charge and a positive charge, so they'll be attractive to one another. And so my force will be in that direction, and my electric field similarly will be in that direction. Okay? You with me? Does that excite you? Yeah. The electric field is just a way to sample the force. It's just really a way to describe the force. All right? It's just sort of this tool that we just make up, more or less. All right. These are vector quantities, so just like we did with forces, you can use the superposition principle to add up electric fields. So for example, if I have two positive charges, I can find the electric field in the middle here. So my electric field due to this particle will be to the left or right at this point in the middle. It's going to be to the right. Remember, I imagine this positive test charge and I ask myself, what is the direction of the force? And then the electric field due to particle 1 is in the same direction. The electric field due to particle 2 is in that direction. Yay? Yeah.
I took you to assume that the thing in the middle is positive.
That's what you have in your back pocket. So we make all of our assumptions based on the idea that this test charge is positive. So it just is positive.
Test charge
is always positive. It doesn't really exist. All right, the positive test charge. What?
Make it whatever we want.
No, you can't make it whatever you want because you have to fall in with the international accords that have been agreed upon.
I thought it was
It's not really our imagination. It's for
Huh?
I thought it was according to our imagination.
Right. The key word being our imagination, not your imagination.
Yeah.
Right, it's always positive. Okay, it's not a real charge. It's just.
I'll try to keep positive thinking.
All right, keep positive. Thank you. All right. So, this positive test charge, it gets a little cumbersome. So we'll just take it away, and you can draw the same thing. So we can say that our electric field in this direction is E1, and our electric field in this direction is E2. And then if we want to know the net electric field, in this case, it's just the vector sum. So the net electric field, due to a collection of charges, this is the net, or you can write it as a sum, as a vector sum, is going to be E1 minus E2, and then that's going to equal my net electric field. So if charges Q1 and Q2 are identical, and you're equidistant between the two charges, what's my net electric field going to be?
0.
0, right. So if charges Q1 and Q2 are identical, and the point is equidistant, that's a word we don't use enough, isn't it? Equidistant. My charge to you today is to try to use the word equidistant in a sentence. Can y'all do that today? Like when you're talking to your friends. Point is equidistant. The electric field equals 0. Consequently, the electric field is defined by the forces. The net force is also equal to 0. That says net, not nah. Okay?
Force gnats.
Right.
Give a lot of it down.
Gnats, right. All right. So as you might expect, we can also do this in 2 or even 3 dimensions, and it's basically the same as what we did with Coulombs Law. I'll set it up, an example for you, but I'm not going to work through all the vector stuff.
That's the difference between the E field and the force is that you're taking like F13 would be taking F1 and F3 together and adding them in, and then the E field is just taking F1. So like if you're working on the equation, it's K1 times K2 over R2.
Right. You just
The
went
electric field is just taking F1.
right.
So you're not taking it together.
Right. You don't include both charges. I'm going to work through an example right now. I'll show you. Because that goes back to when the only difference is finding the magnitude. So that is where this comes in. And this is very important. We'll use this. This is sort of like the Coulombs Law for electric fields. That's how you determine the magnitude of the electric field. And notice that there's only one Q term. That's what you were saying, right?
Yeah.
They just have one Q term. That's right. And that comes about from our positive test charge, the idea of the positive test charge, but the positive test charge is irrelevant because it's not where you go. So let's say, for example, we had this scenario, and we wanted to find the electric field there. We would first draw our vectors and determine our magnitudes, and I'll get you up to that point, and then I'll leave it for you to do on your own. There's a homework problem similar to this as well. I'm going to have 2 electric fields. I'll have E1 and E2. E1 will be the electric field due to this charge. E1, if I were to put a positive test charge right here, that positive test charge would feel a force that would be up and in this direction. All right. And likewise, if that force is in that direction, then that's also the direction of E1, my electric field. It's at an angle theta, which, as we did last time, is equal to this theta. Looks like this is the same triangle we used, so this is a 37-degree angle. Now, the electric field due to this charge, or rather the force on a positive test charge right here, would be to the left or right? It's going to be to the left. So that is going to be my E2. All right, I'm going to go and calculate E1 and E2, the magnitudes. This is just like we did with Coulombs Law. This is the only difference now when we calculate the magnitudes. But basically all the other steps are the same. And in fact, in this example, the angles are all the same too, and the distances. So E1 is going to be KQ1 over R1 squared. And I want to put in my values here. K is 9 times 10 to the 9th. Remember, that's Coulomb's constant. It has Coulomb's constant in it because the electric field is defined based on Coulomb's law. That's fine. 9 times 10 to the 9th is easier to remember and use, but I don't care, you can use it. So what he's saying is Coulomb's constant it has more sig figs than that, but you can just say 9 times 10 to the 9th. It's newtons meters squared per coulomb squared. Q1 is 3 times 10 to the minus 9 coulombs. The 10 to the minus 9 because it's nanocoulombs. Remember, nano is minus 9. Divided by R1 squared. See, somebody remind me what this distance is right here? Right. It's a 3, 4, 5 triangle, so that's 5 meters. So my magnitude of E1 is 27 over 25, which is 1.08 newtons per coulomb. So that's the magnitude of E1. And then you can find the magnitude of E2 as well. So I'll do it right here. This is a charge, 2 times 10 to the minus 9 coulombs. Notice that just like with Coulomb's law, when we're finding the forces, I don't include what with a charge. No, not the test charge. When I write the charge, when I'm finding the magnitude, what have I not included here with that charge? I don't include the negative. Because remember, the negative comes into play when you draw this arrow up here. That's when you take the negative into consideration. Divided by, is that 4 meters squared? So that's 18 over 16. I think it was 1.125, right? Yeah, 1.125. And that's in newtons per coulomb. So that's the magnitude of E2. And then from there, you would find the x, y components of E1. Add up the x components. You'd only have one y component. Use the Pythagorean theorem and the tangent to find the magnitude and direction of that final vector. Alright? I'm not going to do that now, but if you're having trouble with the vectors, you really need to come see me so we can get you past that. Yeah, you'll certainly see vector problems on the test next week. Alright? That's really exciting. I know it's hard to contain yourself, but it's very useful to know how to use vectors, okay? And you'll see them a lot as you go along.
And you also have to find what way it's going, the positive, the partial charge. Also going to find what way it's going to go.
Yeah, you could find the direction that it's going to go. Like, you could ask the same question: what will be the velocity after a certain amount of time? Is that what you're asking?
No, because the charge is going to move, right?
Right. What charge?
The partial, which is working, correct?
The test charge? Yeah, if you let it go, it would move. Am I answering your question? Not really, huh?
I
Okay.
guess what are you looking for? Okay, so once we get to these magnitudes and everything like that, so we're solving for the net force, the net electrical force or field. Is that what we're solving for? So the magnitude of E1.
Right. No, right here we're looking for the net electric field.
So E1, E2 equals the net.
Yeah. Look, I'll just.
E1 plus E2.
Right. We want to know what is the net electric field. I'll go through the steps, but not do the numbers. Is that okay? So it's going to be E1 plus E2. So in the course of that, I have to find the x and y components of E1. E1x is going to equal E1 cosine of 37. E1y is E1 sine of 37. Did I draw them on my free body diagram, they look like this. Let's see, E2 was to the left. And then the Y component of my net electric field will equal E1Y, whatever that value is. And the X component of my net electric field will equal E1X minus E2. Alright, I'm just adding up the X components of the vectors and adding up the Y components of the vectors. And then if I want to find the result, the magnitude of that vector, E net, it's going to be the square root of EY squared plus EX squared. That's this value and this value. And if I want to know the angle for that vector, it's going to be the inverse tan of EY over EX. With the proper, this is from the positive or negative axis, or wherever it happens to be. Is that clear as mud?
So it's basically you're taking the, I don't want to say sum of the forces, but it would be the basis of what you're saying.
The sum of the vectors, yeah.
The sum of the vectors of X, the sum of the vectors of Y coordinate.
Right. The sum of the electric field vectors. Right. We're doing this by hand now, but in practice, this comes up when you're dealing with objects that are charged. Like if you have a charged plate in the lab, for example, you'll need to define what its electric field is, because that electric field is used to move charges. And in order to know how the charges are going to move, you need to know what the electric field is. So we'll get to this soon, but where we want to calculate the electric field due to a collection of charges. This is just a point charge, and this isn't real practical, honestly, because you don't encounter point charges a whole lot. But we'll look at like dipoles, for example, which are very common in the universe, right? Like molecular hydrogen, for example, are different things like a disk or a rod of charge. Those are fairly common to encounter, and they're easy to set up as well. Let's see. Let's watch a little clip. Because electric fields, are used to move charges. And that can be extremely useful because charges are in a lot of things. And so this is one application of it. Let me pull it up. One application where they use electric fields, I don't think that it's actually have begun using this, but they're working on it, where they can use electric fields as a treatment for cancer. This is a TED Talk. You ever watch the TED Talks? They're fairly interesting. Huh?
I saw with
On the electric fields for treating cancer? Oh, okay.
No, but I saw the one on the Vsauce, that they sponsored Michael from Vsauce.
Ah, yeah. Yeah, I like that channel, Vsauce. Let me pull up my playlist here. I need to change my avatar, don't I? I don't know if I can wear it anymore. Huh? Shave it like a guy? I have a headshot from the university. Oh, here it is. We're just going to watch the first few minutes of this, but if you want to look it up, you can just Google Bill Doyle on the TED Talks. He talks about treating cancer with electric fields. Let's see, there might be an ad here.
The speaker clicker society's life is touched by cancer. If not personally, then through a loved one, a family member, colleague, friend. And once our lives are touched by cancer, you quickly learn that are basically...
Hold on, I'll get in trouble with YouTube if I try to put this up, so let me pause this. I want to know where the electric field has its greatest magnitude. At point A, point B, do both of them have the same magnitude, or does it depend upon the distance D?
positive test charge is actually V1 according to AMP.
Mm-hmm. Yeah. I'll stop at 150. About 10 more seconds.
Would you say that A is right in between,
Yeah,
Equidistant.
that's right. It's equidistant between the two charges. Remember, that's your word for the day, right? Equidistant.
I think they just got lazy and got rid of the L.
Yeah.
Equidistance. Equidistance. I think they just got lazy and said, screw the L.
All right, let's see. Most of you put A. I think that's right. We'll take a look and see. With these, you want to be able to draw the relative vectors. Let me show you. At point A, look, I'll call this Q1 and I'll call this Q2. At point A, the field due to Q1 is in this direction, so that's E1. And then the field due to Q2 is in this direction, and it's twice as big as E1. Right? It's twice as big because the charge is twice the magnitude. Notice E1 is away from the positive charge, because if I put a positive test charge, it feels a force to the right. E2, if I put a positive test charge here, it feels a force to the right as well. And so E2 is also in this direction. So that gives me my net electric field. Over here at point B, the electric field due to Q1 is in this direction, E1, and it's quite a bit smaller actually than E1 was over here because I'm further away and I have that inverse square relationship. So the further I get away, the even smaller and smaller my field gets. And then E2 is to the left or right? It's to the left, right. And here my E2 is the same magnitude as it was over here because I'm the same distance from that -4Q charge. Yeah.
so Q1 will still have some impact on point B, even
Right.
Q2 is right there in between. I mean, in
That's right.
this point.
Yeah, over here E1 would have a magnitude equal to K times Q1 over D plus D over 2 squared. It's going to be a small effect, like the electric field, but the further I get away, it's going to be even smaller and smaller, but it's still measurable. All right?
Just curious.
And so which of these has the bigger electric field? Right, A has the bigger electric field. Because I'm adding two vectors in the same direction, one of which, E2, is the same as it is over here. All right. We'll see some more questions like that in the concept test. We'll do that next time. Let me have a few more minutes. So we're not going to move on to the derivations, but we'll get right up to the derivations, which we'll do next time. So most of the time we're going to be doing the electric field due to a regularly shaped object, like two plates, for example. We can find the electric field between them, or like a ring, or we're going to look at a dipole, which you use quite a bit in chemistry. You encounter dipoles a lot, where you have two equal charges, equal but opposite charges. We'll also look at a ring and a rod, I think. No, a disc. These are just charged objects that you can create in the lab just by hooking them up to a simple power supply. But let's just look at something really simple like this hoop, and I want to know what is the electric field in the middle. The way I'm going to do this is like we did last semester when we were finding the moments of inertia. I'm going to break it up into little bitty pieces. Each of the pieces has a charge dq. You remember how we did this? Infinitesimal elements, these differential elements. And then I asked myself, what is the electric field here due to those charges, dq? And so my electric field here, due to this charge, which I'll call dE, is going to be in that direction. And then I can go all the way around. I'm going to take this part over here, and my electric field due to that part is in that direction. You can play this game going all the way around, breaking it up into an infinite number of elements, finding the electric field due to each element. All right? Doing the kq over r squared for each little section of charge. And doing that an infinite number of times. So that'll take a really long time, but you can probably imagine what the vectors are going to look like. So what's your net electric field going to be in this case?
0.
It's going to be 0, because if I go all the way around, I'm just going to get a bunch of vectors that are all opposite in direction but equal in magnitude. So the net electric field, which is going to be the sum of all of those differential elements for dE, since they're all in opposite directions, is going to equal 0. And we're going to do that next time. So the electric field at the center of this ring is 0 newtons per coulomb. And next time we're going to do that for a few different scenarios. Can I go down from here, Rob?
Yeah.
Or you're going to stretch? Okay. I know, we're almost done. I just want to write down the 3 configurations and we'll be wrapping up, okay? So when we're given these distinct point charges, you just add up the electric field due to each charge. That's like what we did. We just say the electric field due to this charge is this, and the electric field due to this charge is this, and then you add those up. But when you're given a continuous line of charge, you divide the object into differential elements. And then integrate to find the total E field. Some of you are just in calculus too, but we did this last semester as well, so hopefully it won't be completely foreign. We're going to consider 3 configurations of charges, the dipole. And for each of them, we'll have to use some sort of different mathematical tricks. Like with the dipole, we'll have to use the binomial theorem. We're going to do a ring, I think. Yeah, a ring and a disk. A charged ring and a disk. The ring that we'll do a little bit differently. We'll take a ring and we'll find the electric field at some point above the ring. And same with the disk, right? There are pictures in your workbook. With the disk, we'll do that. Now these, like we did last semester, you recall, we're going to go with the derivations, and I'm going to give you one of the derivations for the exam, but I'm not going to give it to you on exam day. I'll give it to you on Wednesday. I think that'll be enough time. All right, I'm just going to look for y'all to memorize it. That's what I expect. But it's a useful thing to be able to do these sort of math tricks. But all right, y'all have a great day. Thanks for hanging in there.